Hello and welcome to Red Pitaya video project tutorials. Today we are going to show you some interesting project that we are working on. In the next following weeks we are going to make some more that we hope you're going to like. So let's make a short introduction to our topic. Electromagnetic compatibility tells us how certain devices emit unintentional electromagnetic energy and how others respond in an interfered environment. Today, we are going to perform magnetic field radiation measurements, which is part of unwanted electromagnetic emissions. So, we will be using Red Pitaya that we have here with additional simple circuit and of course a pickup coil for detection. Circuit sits on Red Pitaya extension connectors, but let's talk about this a bit later, and if you would like to make one on your own, you can find the documentation in the link below. We will hold a coil above home appliances and electrical powers in power line. Their magnetic field will induce voltage in the coil and it will be measured by Red Pitaya. Magnetic field will be graphically presented directly in the Red Pitaya Teslameter application interface on our computer. Teslameter is application available in Bazaar and it can be installed with just a single click. Now, let's look at the theoretical background of this experiment before the fun begins. Voltage is induced in coil by changes in magnetic field according to Faraday's law of induction. It states that induced voltage in any given time is equal to negative derivative of magnetic flux. For sinusoidal signal, this equation can be used to calculate induced effective voltage. The higher the frequency or magnetic flux density, the higher the induced voltage. Our coil has 210 turns and a diameter of 15.6 cm. It's wound on plastic base that is attached to the handle for the sake of convenience. For example, at 100 Hz, induced voltage is 5 mV and 500 mV at 10 kHz, at the same magnetic flux density of 2 microtesla. In order to see the correct form and amplitude of magnetic flux density on Teslameter, we need to integrate voltage signal from the coil. An operational amplifier integrator is the solution. It acts as first-order low-pass filter, that means that amplification is lower at higher frequencies, so output voltage amplitude is the same at the wide frequency band. In the web interface, we input constant for coil and low-pass filter. The constant K is calculated from coil and filter parameters. Because of imperfect circuit implementation for the desired frequency range, K is not really a constant. But for this measurement, with a small error, we can use the mean value of K. In our case, K is 4.5 times 10 to the minus 6 power Tesla per volt peak to peak. At the input point of amplifier circuit, there are two range selection switches for selecting measuring range. Switches engage attenuation of voltage signal from coil. At default range, maximum displayed magnetic flux density is 2 microtesla. With switches we select either 1 to 10 or 1 to 100 attenuation. With that, we get measuring capability up to 20 or 200 microtesla. If we get too high measurement on lower range, we continue measuring on high range. Range selection is also needed on web interface to display correctly scaled values. With that circuit, we go and measure leaking magnetic field on some household appliances. According to the ICN, IRP and EU policies, there are two limitation value areas of the magnetic field density for the constant human body exposure. Increased sensitivity area is limited at 100 microtesla RMS, and professional exposure 1 reaches 500 microtesla RMS. We will try to figure out if the gadgets we use in our everyday life comply with those standards and are considered safe. So, how about we move to the fun parts now? Let's measure something we use in everyday life, like light switch for example. We are going to measure magnetic field in wires near them. Let's start with the switch turned off. All the readings here are just from interference of other cables and devices. So what's going to happen if we turn one of these on? Did you see? Actually, it's quite a change. The waveform we see here on the Teslameter is a representation of current flow through the wires. It isn't a pure sinusoidal form. That is because of higher harmonic frequencies added to the primary one. Now let's see what is going to happen after turning the second switch on. See, the change is actually considerable again. So how strong is the field? Let's say it's 2.6 microtesla. I wonder what will happen if I move the coil away from the wall. So the field is decreasing very fast, right? We can say that the field is strongest close to the surface and drops rapidly with distance, falling away substantially over the first meter from the appliance. So, all of this work made me a bit hungry. Let's see how hot induction stove performs in electromagnetic emissions. I think that among other household objects, actually it has the highest level of electromagnetic emissions. I wonder if Red Pitaya agrees with me. I'll switch to our middle range of 20 microtesla. See, 20 microtesla range still isn't enough. Let's switch to 200. As you can see, induction stove really emits strong radiation, more than 150 microtesla. Lots of magnetic flux is escaping in environment. Lucky for us, induction stoves detect whether the cooking pot is present or not to prevent the excessive magnetic radiation. And now let's go and grab some fresh air. Here we are at electric cabinet and the lower range is already clipping. Let's switch to higher range to reduce sensitivity. It looks like 5 microtesla. Now let's go to the power line. Here we are near the power lines, and some people are quite afraid of this. As we can see, maximum reading doesn't exceed 2 microtesla. Magnetic field depends on current in wires. It varies through the day, as power line is not constantly loaded. Well, that was interesting and informative. We can conclude that all of the appliances comply with standards, and that the biggest source of magnetic radiation came from the induction stove. Power line is also nothing to be afraid of, well, at least regarding the magnetic fields. So, graph, code modification and other relevant stuff for Red Pitaya you can find the link below. And if you wonder what's the magnetic emission for the hairdryer, make your own Red Pitaya Teslameter. Goodbye!